I would like to invite Dr. Larry Anderson to present the perspectives of new vaccines for respiratory viruses. O Dr. Larry Anderson, ele trabalhou no CDC durante muitos anos, chefiando o Departamento de Vírus Respiratórios e Gastroenterites do CDC, nos quais estavam também os vírus como sarampo, rubéola, cachumba, pólio, e então ele tem uma grande experiência nessa área, e atualmente ele está na Universidade de Emory, no Departamento de Doenças Infecciosas, na Pediatria desta universidade. Uma questão que eu gostaria aqui de ressaltar em relação ao Larry é que nós temos toda uma geração de pesquisadores aqui na Fiocruz, como eu, o Edson, o José Paulo e vários outros, também na USP e também outras universidades do Brasil, que nós passamos um tempo de nossa vida lá no CDC, no departamento que o Larry chefiava, e foi assim bastante gratificante de ver como ele nos recebia, o apoio que nós sempre recebemos dele e do pessoal do departamento dele para os nossos trabalhos e para o nosso desenvolvimento. A gente foi muito jovem para lá, e para o nosso desenvolvimento pessoal. Então, o Larry ele tem aqui no Brasil um fã-clube, e aí eu gostaria, assim, estou muito feliz de estar com ele aqui. Larry, please.
Thank you. Thank you, Marilda, and thank you for inviting me to participate in this meeting, which I've enjoyed what I can understand. And it's been nice to come back to Rio, and also visiting and thinking about some collaborations in the future. What I'm going to talk about is respiratory vaccines. I'm not going to do an exhaustive review of respiratory vaccines. What I'm going to try to do is highlight vaccines which I think are examples of interesting, novel ways to approach vaccine development. So concepts are probably more important than the content. This is my list of respiratory viruses, and vaccines have either been developed or are being developed for each one of the viruses, with the exception of vocavirus, which is a good thing, because there probably wouldn't be a good reason to make a vaccine for that. For the coronaviruses, the vaccines have been for SARS and MERS, and then the other viruses are being developed at various stages in various ways. Now, I'm going to talk about adenovirus, influenza viruses, rhinoviruses, and RSV. RSV because that's my favorite virus. So I've already told you that. So starting out with influenza, which would be the most important of the potentially vaccine-preventable diseases among the respiratory viruses. I might put RSV in there ahead with young children, but overall probably influenza. And I think we've already heard some talks that address some of the issues with the efficacy of influenza vaccines, which in a good year is about 50–60%. You've got the problem of antigenic drift, which you monitor, surveil viruses, try to predict what the next vaccine or next circulating virus is likely to be, and make the vaccine based on that. There's a problem of insufficient antigenicity, immunogenicity, or at least protective efficacy, which may not be all the same. With increased antigen dose in the elderly population, clearly having an increase both in terms of antibody response, and now I think there's reasonably good data that it's also improving prevention of disease, including mortality. There's other components of the vaccine that may be important or be able to contribute to protection from disease. And I'm going to talk a little bit more about that, not so much in influenza, but RSV, that concept. The difference in cell culture versus egg-grown virus for live virus or for the vaccine, inactivated vaccine. One of the problems is that you can get some mutations that alter the antigenic structure sufficiently to possibly affect the match with the circulating strain. And with the live inactivated influenza or live attenuated influenza virus vaccine, you have a problem with the immunogenicity, or at least the immunogenicity, the H1 component. The other part of influenza is preparing for pandemic influenza, which is kind of the gorilla in the room. And presently, there's a lot of work doing anticipatory vaccine development, looking at viruses that have gone from avian, the birds usually, come into humans and cause disease, including some with very high mortality, and developing a vaccine that would be ready in case the virus actually acquires the ability to transmit efficiently in humans. Another approach, which I'm going to talk a little bit about, is inducing broadly reacting antibodies. And that concept follows from sequence studies of the viruses and the fact that one part of the hemagglutinin molecule, the stalk or stem region, I'm going to use those terms interchangeably, is common among the group 1 influenza viruses and group 2 influenza viruses and the influenza B viruses, which allows you to think about 3 antigens that might provide broadly protective immunity. And there's been really 2 approaches that I'm going to talk about. One is developing a vaccine based on the stem part of the hemagglutinin molecule. And the reason for doing that is if they have the whole molecule, the head, the variable region, predominates in terms of inducing antibodies. And most of the antibodies are made to this region. The stem or stalk region has more conserved epitopes, which monoclonal antibodies in a variety of studies have identified. Not a lot, but some. And naturally, some humans induce antibodies to this region. So they've taken 2 approaches. One is to make just the stalk or stem as an antigen and immunize with that. The problem there is stabilizing it such that you can actually use it as a vaccine. If you chop off the head, it's unstable. The other strategy that people have used is use a common stalk and variable heads, with the idea that focusing on a memory response will enhance, improve, focus antibodies, the broadly reacting antibodies in the stem region. So first, looking at broadly reacting antibodies, and this is just to show that they've been able to demonstrate that this works in mice, in ferrets, and in primates, that you can take, in this case, using 3 different heads with the same stalks. You have 3 different viruses, 3 different times. When you do that, you increase stalk antibodies, and this is looking at protection in ferrets, and you get, and what you see is the vaccine is red, has better survival than the positive control inactivated virus. Well, it's the same as an activated virus with the match. The negative control, which you prime without the head protein or without the stalk protein, and just the construct, the influenza B virus in terms of this time, which is actually used as a virus vector. So you can see that you get good survival with the red, and with a heterologous challenge virus. In this case, H5N1 virus, when you use H1N1 here, or the H1 virus when you use the H5N1 as the third dose. So this is H1 challenge, and this is H5 challenge. So that's the sequential immunization with common stock and variable head regions. The other strategy has been using structure-based design in a sequential fashion to get a stabilized stem antigen. And what they've done, and I'm not going to get into the details, is look at the structure, use biochemistry to stabilize that structure, the stem region, use crystallography and monoclonal antibodies to see if they've maintained, how well they've maintained structure and antigenicity. And using those sequential steps with a combination of stabilizing insertions, mutations, and deletions, come up with a product that they then have used as a vaccine immunogen. And this is just looking at antibody response. And I think the interesting piece, the bottom two rows are ferrets, the first one is mice. And the part that maybe is most interesting, first of all, you get good antibodies, binding antibodies that react broadly against different HA molecules within the same group, illustrated in here in mice and here in the ferrets, not quite as high comparability. But you get lower neutralizing antibody response. So it's not as effective. These antibodies bind to the stock, are broadly reactive, but not as effective in vitro neutralization. Now, when you look at protection, on the other hand, it's actually quite good. And on the left side, you're looking at weight change, so disease, and the right side, survival. And this is the head vaccine, and this is controls. So it actually is effective in mice, and then this is in ferrets, with challenge heterologous virus, even though you don't get such good in vitro neutralizing antibodies. And part of the reason for that is some of the neutralizing, in vivo neutralization is non-classic, well, it's not non-classic, but it's not measured by in vitro neutralization. It's Fc dependent, so you get antibody-dependent cytotoxicity or immune complement mediated neutralization of ours. And it's the other half of antibody-mediated enhancement of infection, Fc receptor related. So another thing, and this is, they've done some work with influenza, and this is more in the future. Is this going to help us get design and make vaccines quickly? And it's message RNA that you get into the cell that then translates the associated protein for a vaccine. They've also used it to make immune globulin as a prophylaxis. Now, the advantage of it is you can, if you know what protein you want to immunize, and you do have to know that or it's not going to work, obviously. You can make the message RNA very quickly, and you can produce quantities quickly. And once you establish the safety of the basic methodology, which has not been done yet, then you have potentially a relatively quick way to make a vaccine or an immune globulin much more rapidly than existing technology. So this, I think, is a potentially very exciting technology, underlying potential, because they've got a way to go to prove that it actually is going to be a viable alternative. Now, this is kind of what the strategy looks like schematically. And this is with Zika virus. And I'm not talking about this because it's Zika virus, although clearly Zika virus is important to Brazil and as emerging infection. But it's a recently published article using this methodology to vaccinate mice as well as primates. And the strategy is you make them design the messenger RNA, and you include some nucleosides that block the innate response to the RNA and enhance the translation into protein. So then they have to get some way to get the messenger RNA into the cell. And this is just saying they can get it into different type of cells. They produce the protein. Here it's in the supernatant. And one of the things about the supernatant with Zika virus, when you produce pre-M and E, or the envelope protein, together, you get pre-virion structures, virus-like particles, or pre-virus-like particles, which are probably pretty good immunogens. So they get it in the supernatant, at least in some of the cells. So then, does it work? And I think this illustrates, they're looking at two different mice species, black 6 mice on the top and Balb C mice on the bottom. And you're looking at T cell responses at the top. So you're looking at restimulation of spleen T cells and looking at percent interferon gamma positive, TNF alpha positive, or IL-2 positive. And what you're getting is you're getting a T cell response with 1 dose of this vaccine, I think this is 4 weeks, or it's actually 2 weeks after the immunization. Then you're looking at the antibody response, and we'll just look at this panel here, and you're looking at 2 weeks, 4 weeks, 8 weeks, 12 weeks, binding antibody to the E protein. So you're getting a very quick and pretty high titer antibody response to the E protein based on ELISA binding. You're also getting neutralizing antibody in 2 different assays, a plaque reduction neutralization assay, and the second one is a pseudovirion assay with the Zika N protein, and the same data in the mouse. So this actually does work, and their comment was that it induces much higher titer antibody than DNA vaccine. This is with 1 dose of the vaccine, which means if it works this way in humans, you can get a very rapid response to the immunogen and a fairly high titer. Now, they don't have long-term antibody. At 12 weeks in rhesus macaques, they had persistent antibody, so they're at least at that stage thinking that you may have longer-lived antibody. They also looked both in these mice and in rhesus macaques for preventing disease, and I think this was at 4 weeks after the immunization. Challenge with Zika virus, and the controls had relatively high titer Zika RNA in the blood, and the vaccinated animals, both the mice and the rhesus macaques, didn't. One of the rhesus macaques had a very just detectable level of viral RNA at the earliest time point, but not afterwards. Now I'm going to switch to adenovirus vaccines. Now that's the other actually licensed respiratory vaccine, and I'm going to do that for one reason. It's an interesting way to develop a vaccine. Now, adenovirus vaccines were developed because of the problem of adenovirus 4, 7, 3, 14, and 21, less commonly, causing febrile acute respiratory disease during basic training camp. When the recruits are stressed, they're living in very tight, close quarters, and in outbreaks, they've had up to 50% of recruits hospitalized with febrile respiratory illness. So it's a real problem in disrupting their training process. So in the 50s, in some studies that would never be done now, but in prisoners, they looked at droplet size, aerosol versus aerosol, lower respiratory, upper respiratory, in oral administration of adenovirus and rhinovirus. In adenovirus, very interestingly, they found that if you gave it droplet or aerosol, you got disease, fever, upper respiratory symptoms, and actually lower respiratory tract symptoms as well, including pneumonia. When you gave it orally, you had no symptoms at all, but you did get an antibody response. So the vaccine that they use for the military, adenovirus 4 and 7, is not attenuated. It's attenuated by route of administration. It's given orally, and it's actually been exceedingly effective. And I think they had the vaccine, they decided to not support continuing the vaccine. They had reappearance of the febrile respiratory illness, and when they reintroduced the vaccine after they went through the clinical trials and so forth, they've had a 75% decrease in overall febrile respiratory illness during training, basic training camp in the United States. So it's very effective. Next, I'm going to switch to respiratory syncytial virus. And RSV was discovered in the mid-1950s. It was very quickly recognized as a major cause of severe lower respiratory tract illness in young children. And as illustrated here, you have a peak of disease much earlier than for most other viruses. Despite the presence of maternal antibody, you still get disease, particularly in the less than 6-month-old, even younger. The 2 to 4 month is probably the peak month of time of disease. So it was recognized as a major pathogen. RSV also causes repeat infection throughout life and contributes to substantial disease in elderly populations, individuals with compromised immune system, along with all the other respiratory viruses. So it can be a significant problem. At this point in time, there are vaccines being developed for 4 target populations, with the one of greatest interest being the young infant, the one that's most likely to achieve success in the near future is vaccination of pregnant women to protect their infant in the early months after delivery. There's good data that higher titer of neutralizing antibody from mom delays disease, decreases hospitalization in the young infant. So if you can increase titer, you can delay the disease to a little bit later in life when the child is probably better able to cope with the infection. And then the elderly population, there's been some studies there. Unfortunately, no vaccine has yet succeeded. Now, the first vaccine actually caused more severe disease, formalin inactivated vaccine, and young children who got this vaccine ended up with higher rates of hospitalization, 1 or 2%, or up to 60%. A couple deaths were associated with subsequent infection in vaccinated children. So that's been a major problem. Now, that was felt to be possibly route of administration of the vaccine, probably the formalin activation of the proteins, and a Th2 biased versus a Th1 biased T-cell type of response, memory response induced by the vaccine. Well, this has meant directed which types of vaccine you can use in different populations. And essentially for the young child, at this point in time, the only viable candidate vaccine is a live virus vaccine, either a live attenuated respiratory syncytial virus or a virus vaccine vector, which has been given. And live virus doesn't cause enhanced disease. It provides some protection. So this just reiterates that point. Well, because there's been so much problem developing vaccine, you go back to the virus. What does the virus look like? What does it do? What's the pathogenesis of disease? What are the different proteins doing? And which of these proteins might be relevant to vaccine design? And whether you're looking at a live attenuated versus an inactivated vaccine or subunit vaccine, how you think about that question is different. So in response to that, a lot of different proteins have been thought about in RSV vaccines with live attenuated. There, the focus has been attenuating the virus such that it's not going to cause disease in the highly susceptible young infant, and in some cases, enhancing the immune response. And I'll talk just a little bit about that because that's one of the recent vaccines. For the subunit vaccines, the focus has really been on the F and G protein, which are most effective at inducing protective immunity, with F being most effective at inducing higher titer neutralizing antibodies, protective immunity in animals, and also cross-protection. The G protein is more variable, which creates problems in terms of using it, potential problems of using this as an immunogen to protect a population, whereas the F is relatively conserved. This is one of the candidate vaccines that is being pursued, and that's looking at a delta M2 deletion. That particular protein modulates the switch from transcription to translate protein to transcription to replicate the virus. When you take this out, you get less virus replication, more protein production, and as illustrated in this slide, looking at the neutralizing titer with the M2 deletion versus the non-M2 deletion, you get higher titer of neutralizing antibody, and you actually get better protection in terms of the peak nasal wash titer. So it's effective in the animal model. Whether it will be effective, that right balance in attenuation versus attenuation so you don't cause disease, and sufficient immunogenicity to be effective, time will tell. One of the more exciting developments is really structure related. Similar to the influenza, looking at the structure of the proteins has allowed individuals to develop proteins that address specific issues. In this case, for RSV, the fusion and entry is based on flipping the F protein from the pre-fusion to the post-fusion form. Now, flipping from the pre-fusion to the post-fusion form, in general, can happen fairly easily, naturally. So a lot of the virus preparations and antigen preparations that have been used to immunize have been post-fusion versus pre-fusion. Now, the problem with the post-fusion versus pre-fusion is there's more neutralizing epitopes on the pre-fusion than the post-fusion. Some epitopes that neutralize in the post-fusion, they neutralize in post-fusion if they're also present on pre-fusion. And there are some that are conserved. Palivizumab, for example, is present on both pre- and post-fusion F proteins. So if you have binding to the F protein in the post-fusion, it should not neutralize virus because that protein cannot fuse membrane and allow entry. It could conceivably neutralize by other mechanisms, but not by classic in vitro neutralization. And this just shows that, in fact, if you have a pre-fusion stabilized, looking at the structure, they're able to identify mutations that would stabilize the protein in the pre-fusion form. When they do that, both in mice and in rhesus macaques, you get an increase in neutralizing antibody, with the post-fusion being here, in different flavors of stabilized pre-fusion F proteins here, with these two also given in the rhesus macaque, with about a half to a 1 log increase in antibody titer. Now, with this, looking at the proteins and thinking about ways to design vaccines, there's a lot of vaccines being developed, and this is a slide that PATH has developed in terms of trying to help facilitate and understand where vaccine development is. And I'm just going to highlight the ones that are in phase 1 or later clinical trials. And the Novavax vaccine was tested in a phase 3 trial in elderly adults and failed. They are proceeding with that vaccine in pregnant women with the idea that even though, I mean, they did boost antibody, that boosting antibody in mother that's then transferred to the fetus is a lower bar. You're not looking at immunizing an already pre-immune population. That population is actually going to have a variety of immune responses to RSV, cellular in addition to the antibody responses. So that's moving along. There's other F protein flavors. There's the live virus M2-2 deletion mutant. That's in clinical phase 1 trials. There's some adenovirus vector producing F vaccines in phase 1 and 2 clinical trials. And one of the interesting things is using monoclonal antibody prophylaxis in lieu of a vaccine. And that's based on, on 2 products now that are doing that, where you give an antibody that has a longer life than the classic palivizumab, where you need monthly injections, with 2 strategies to achieve that. One is to increase the avidity, affinity, and neutralizing capacity of the antibody such that as it drops off, you still have sufficient protective efficacy to prevent disease. And that's the Regeneron molecule. Now, the MedImmune product has that. In addition, they've mutated the FC part of the molecule to increase the half-life of the antibody, and 1 dose of this antibody should last for an RSV season. So they're actually developing that as, quotes, vaccine candidate, even though it's passive immunity. The idea there, you get the child through the first high-risk year, and then they'll pick up and develop their own immunity and do okay. Now, we've looked at it, and this is the one little bit of studies that we've done I'll talk about, from a little different perspective. And that's based on studies that we've done with the G protein of RSV. And you get neutralization in vivo, but not in vitro, and it's FC mediated, so that's the ADCC and complement-mediated neutralization. It's actually quite effective in vivo in the mouse. Now, what it does in humans, I'm not quite sure because we haven't done those experiments yet. But it does do that. The other thing that the G protein is associated with inducing host responses that contribute to disease. So it's kind of a bad actor in RSV, and probably one of the reasons, and our data begins to look like it's kind of the bad actor that leads to the reactive airway disease that we see with RSV. So that's a concern. On the other hand, it's also an opportunity, because if you can bind the G protein and take it out of the picture, theoretically, you might take away that part of the disease. Now, I'm not going to talk about those studies, but we've looked at monoclonal antibodies that bind G, and in fact, we can do that very effectively, either as a prophylaxis or as a treatment, and it's actually more effective in a treatment model than palivizumab. Similar levels of neutralizing virus, but the anti-G monoclone will shut down the weight loss, the airway reactivity, mucus production, and decrease bowel cell infiltrate much more effectively than palivizumab, or just neutralizing the virus. So the virus does a lot of things. It kind of sets the table to survive and replicate. And some of the things that it does, in addition to just entry and replication, alters the immune response and other things that contribute to disease, which provides, in a sense, a potential Achilles heels in the disease side of what the virus does. The other thing the G protein does is modulate host immune response, which is kind of that disease pathogenesis piece. But particularly the innate response data on macrophages and dendritic cells that the G protein alters their response. So with the goal to decrease disease, will the G protein provide an opportunity there? Well, looking at the G protein structure, it's a highly variable protein, but there's a part of the protein in the central region which is conserved, some of which is 13 amino acids conserved among all RSV strains, and then a larger region, about 155 to 190 or 155 to 206, that's conserved within the group A and the group B, the two major groups of RSV. There also is a CX3C motif. That motif is a chemokine motif, fractalkine being the chemokine, and RSV actually binds to the G protein binds to that chemokine receptor, CX3CR1, and you can neutralize infectivity to some extent by blocking this binding. The other thing is, although in vitro, in classic tissue culture, continuous cell lines, CX3CR1 is not important as a receptor. When you have primary human airway epithelial cells, it actually is an important, not the only receptor, but an important receptor. In our hands, it's responsible for about a half of the cell infections. So it's a receptor in the primary human airway epithelial cells, and presumably an important receptor in natural infection. So anyway, so that's the background. So what we're looking at here, and I'll go back to this. If you look at this region, Tom Umans and Marty Moore, Oklahoma State and Emory, used reverse genetics to develop two CX4C viruses for us. Everything else is the same, other than an alanine inserted right here. With that alanine, the G protein no longer binds to CX3CR1. And we've looked at that protein or that virus in a number of different settings, and it does alter the type of host innate type response you get. So we wanted to see if you put that into a live virus, does it attenuate the virus in terms of disease? So this is a series of studies looking at that. And what you're seeing is the wild type recombinant 19F. And we use that virus because it induces mucus production and airway reactivity in the mouse model. So it's got a stronger manifestations of disease more similar to what you see with natural RSV infection. The A2 strain and some other strains don't. There are other strains that naturally acquired strains that do induce this. So we've got the wild type virus, then we've got the CX4C virus, and you lose about a log titer of almost a log, well actually about a half log, it's less than a half log, about 2.4 with this one. When we first did it with the same inoculum, we had about almost a log decrease in virus titer. So we wanted to see the effect of the CXC4 mutation independent of virus replication. So we increased the inoculum for the CX4C virus and had less difference, still some, but less. This gets back to the antibody-mediated or antibody ADCC FC-dependent neutralization or lack of neutralization of virus. So here we're looking at 131.2G that binds proximal to this site, prevents binding to CX3CR1, and see how well that does in altering the disease process. So then we're looking at a number of different manifestations of disease. We looked at virus replication. Doesn't replicate quite as well as the wild type virus, but not a whole lot difference. And what you see here is the 131, the recombinant virus, or the wild type, well, this is A2 virus, and the recombinant 19F virus and the CX4C virus. But the CX4C virus has no weight change, and the wild type virus does. When you look at bowel cell infiltrate and you're looking at wild type A2 virus, recombinant 19F virus, and the second and fourth bars are the CX4C virus. So in all the slides, what you see is fewer bowel cells, no effect on breathing effort, which is a manifestation of restrictive airway disease, and then mucus production. You get some with a 4X virus, but substantially less than you do with a wild type virus. So that single mutation markedly decreases disease in the mouse. Now, we also wanted to see how it affected the immune response. And this is looking at IgG and neutralizing antibodies, and then antibodies to that central conserved region of the G protein. There we wanted to see if we still induced antibodies that bound to this region, even though we had this CX4C mutation. And what we found was that even though we had a little bit less replication, the CX4C virus induced higher titers of, and this is relative, so it's not the actual titer, it's the difference in titers was substantial between ELISA and neutralization. To put it on one slide, I basically gave the ratio of wild type neutralization to wild type neutralization, or recombinant, or the CX4C virus to the wild type virus. So the wild type virus is always 1, and then if it's, in this case, about 1.5, you've got a 1.5-fold increase in neutralizing titer at 75 days after infection. Similarly for IgG, and we also had good response to that central conserved region of the G protein. We also looked at the T cell response, re-stimulating spleen cells and looking at the intracellular cytokine response. And what we're looking at is TBET, which is a transcription factor associated with Th1 response, interferon gamma, which is associated with the Th1 response, and IL-4, which is associated with a Th2 type response. And what you see is the wild type virus is lower for TBET and interferon gamma than the CX4C virus, or the wild type virus when you add the monoclonal antibody that binds the G protein. And in contrast, that has a higher IL-4 response, percent positive cells, than the CX4C virus or the wild type virus with the monoclonal antibody. So you're switching, you're getting a higher titer neutralizing antibody, switching from a Th2 to a more Th1 type response and less disease, which I think makes it promising as a mutation to include in a virus vaccine. In terms of attenuation, the level of attenuation in the mouse presumably would be more independent of any other attenuating mutations, which likely you would want to add with a live virus just because it blocks binding to CX3CO1. How am I doing this time? Okay. Fine. Okay. Quickly then. Rhinovirus. Now there's a lot of rhinoviruses. And people basically say there's no way you can make a vaccine to rhinovirus. You don't have common antigens, at least that have been identified, and there's no way you can make a vaccine against rhinoviruses. There's not a consistent genotype, and they genotype now because it's much simpler than doing hundreds of cross-neutralization assays. But Marty Moore down the hall from me said, well, let's think about this differently. And he looked at the literature, and you have been able to induce protection in humans and challenge models with an inactivated rhinovirus vaccine. Now, rhinovirus is a picornavirus. It's in the same enterovirus genus as poliovirus. It makes sense. You can inactivate poliovirus and have a very effective vaccine. So then he thought, well, what happens if we increase the valency of the vaccine? And this slide illustrates that point where he's looking at one valent, so it's HR16 neutralizing antibodies when that's the only component of the vaccine. And does that decrease titer when you increase to 3-valent, 5-valent, 7-valent, and 10-valent? And it really did not significantly decrease the titer of neutralizing antibody induced by the vaccine. So then, well, let's try 50. Okay, so this is 50, and you're basically looking at the light bar is first dose, it's a 2-dose, he's using 2 doses, and kind of summarizing a lot of data with the red bar being above the background noise, and about 1 to 8 titer has been thought to be associated with protective immunity, although there's not that much data on that. But what you see is that with one exception, 49 out of 50 got a good antibody response to the vaccine. So this multivalent vaccine is a potential. Now, would there be a use for a rhinovirus vaccine? Well, the common cold is probably the most common infection of humankind. It certainly causes a lot of symptomatic disease. Possibly more important is rhinovirus exacerbation of asthma. And it's a substantial contributor, maybe 30–40% of asthma exacerbation. So and asthma, of course, certainly the pediatricians would know that that's a major cause of disease and hospitalization. So there's a real potential here for this. Last, this I think is a potential game changer. And this is a microneedle patch. And the idea is that you have these small little needles on a patch, and this could be the size of a dime or a nickel, whatever, in the US. And then you put the vaccine on the needle or inside the needle. Now what he's doing is putting it on the needle. And then they've gone through a whole series of trials, and it actually does work. It actually seems to have almost an adjuvant effect. So when you vaccinate, it's like putting a Band-Aid on. So the technology is low technology. And if it works, this could be a major advantage generally in immunization, but particularly for the eradication control programs where oral vaccination for polio is easy, low technology. An activated vaccine with a needle is not. You got a substantial disposal problem. There also is a storage issue and transportation issue. It can be stored at room temperature because the vaccine is basically lyophilized instantaneously because it's such a small volume on the needle. And you put it on the patch and off you go. So and this is a study in influenza that's published a while ago. There's a clinical trial that has not come out yet. I guess it's in review in the journal. But you're looking at HI antibody at 14 and 28 days in the adult and the young. And this is, the red is, the blue is microneedle and the red is the IM dose of vaccines. You're comparing classic immunization to the microneedle vaccination. And what you get is as good antibody response in terms of the adult, but actually in the child, you actually got a better antibody response. The other thing it tended to do was switch a little bit towards, and this is in the mouse, a Th1 versus a Th2 phenotype of the antibody response, with Th1 one being IgG2A more than IgG1A, for that. Let's see. And this is looking at protection, and you're looking at weight change, the survival, and lung virus with microneedle, IM, and this is young children versus adults, so they're looking at the young children. So blue is microneedle, red is IM, and green is nothing. So this is without any vaccine weight loss. You get more weight loss with the IM versus the microneedle. Survival, the IM does better than the microneedle does better than the IM, blue versus red versus green, and you have a lower titer of virus in the lung. So this is a very promising candidate. Now, why hasn't it taken off? This has been around for a while, and it really has to do with cost of changing a vaccine, because if you go from needle to a microneedle, you're basically changing the vaccine and have to re-go through the licensure process, or at least part of it. So the vaccine manufacturers have no particular reason to go after that. And for new vaccines, it adds another variable. And if you're moving forward with a new vaccine, you want to eliminate variables to get there rather than add variables. Now, how do I think it might get there? And I think it has to do with the global eradication programs for measles and hopefully for polio. I think for measles, this is the missing technology that would make it possible to do measles in terms of the technology for administering the vaccine, some of the cold chain issues, and the disposal issues, which are not unsubstantial in terms of tons of needles for a vaccination program. And this is basically dissolvable. You can throw it in the toilet and it's gone. Now, where are they? They're beginning, well, they've completed phase 1 trials of influenza, Georgia Tech and Emory, and they'll be published sometime in the not too distant future. They're going to begin phase 1, 2A trials with measles. They've been able to get measles virus onto the needles, maintain viability, and induce response. And they're moving into phase 1 trials. Inactivated polio vaccine, again, they've gone through the basic studies to demonstrate they can get the antigen onto the needle, have immunogenicity, maintain that immunogenicity, and are going to see how it does in human trials. This, I think, is a real potential game changer in immunization, and I think it's something that sometime in the hopefully not too distant future you will begin to see put in place. And I'm going to thank you. Obrigado.
Larry, thank you very much for this excellent presentation. Nós estamos abertos para as perguntas.
Well, thank you, Dr. Anderson. It was very exciting perspectives here for influenza, for adenovirus, for RSV. These are big problems, and it is very exciting. About the microneedles, they are very interesting, but we need to wait for the human trials.
Absolutely.
So we did here a study in partnership with PETH on needle-free injection. We were very happy at the beginning, but at the end we were not so happy. So I would like to have a better experience in the future with the microneedles. And I wonder why respiratory infections have not more vaccines by respiratory route. I remember studies with measles, rubella by aerosol, and they worked very well. And I think this field has not progressed much. I don't know the reason. So I would like to ask you, why not more respiratory vaccines, aerosol vaccines for respiratory disease? One question. And another one is to add a problem that we have in Brazil is tuberculosis. We have not a good vaccine for tuberculosis, and we would like to have. Do you have any perspective of a vaccine for tuberculosis?
Well, the last question, I'll pass on TB. I know very little about TB, and I know that there's work on that, and I think that's a challenge in terms of understanding the pathogenesis of disease. I don't think anybody has a good sense of what protective immunity is. I think BCG provides some kind of protection, but incomplete. So I would leave that to the TB experts, I think, that jumping in there would not be wise. I think the concept of not skepticism, but let's wait and see is absolutely appropriate. I think if you take the world of RSV, over the years, we've had a number of people say, we've got the answer. Well, they didn't. I think until you actually see the studies and demonstrate that it works in humans, certainly for RSV, and I think that's also true for the microneedles. I think with the microneedles, my enthusiasm is because so far it's looked good, but that final step has not been taken, and that's absolutely appropriate. In terms of respiratory vaccines and a route of administration, the live attenuated RSV vaccine is given intranasally. And they tried measles, and there was some concern about the fact that it might provide an easier access to the CNS, which didn't prove to be a reality. But I think, to me, the aerosol administration of measles is maybe easier, wasn't more immunogenic. I don't know that they really had efficacy data on it. And to me, you're doing an incremental increase in vaccine delivery potentially, whereas microneedles, if it works, is a game changer. And I can't see investing in a little increase in a vaccine because you have to change how people do things, and that's not easy. So I think the upper respiratory tract is a route that is being used for the live RSV vaccines. Obviously, adenovirus, you wouldn't want to do that because you don't have an attenuated virus and it causes disease. The other viruses, human metapneumovirus, the parainfluenza viruses, the ones that are being actively considered as kind of the classic human respiratory pathogens, are kind of waiting on the shelves. Because RSV, if you get an RSV vaccine, they can tag along. But the amount of disease and the interest in pursuing that independent of RSV has not been there yet. But the same types of vaccines are being considered, live attenuated and subunit vaccines. So the live attenuated would presumably be given intranasal, I think. So.
Thank you.
Larry, the microneedle for measles and rubella, those are presumably live. Is there some trick for keeping the vaccine on the microneedle, presumably in a dry environment, without losing viability? And what about the dose? Can you get enough dose with a microneedle?
Well, I'd have to go back to the specifics of the studies in terms of dose and so forth, but what I've garnered is that you maintain viability pretty well, actually. You can actually
like
take...
you got a lyophilized product?
It's lyophilized.
Like
It's such
Yeah.
a small volume and surface. It's lyophilized instantaneously. So it's like a lyophilized product. And if you maintain temperature, it's actually quite stable. Actually, you can maintain viability of RSV and other viruses on filter paper that's been dried
really?
quickly. Yeah, punch it out. So it's the lyophilization and the fact that it's a surface area with a small volume, that it's instant. It's basically a lyophilization.
I shouldn't have said RSV. I meant rubella. Sorry. Measles and rubella were on
Well, I
the-
know you mentioned
but-
rubella,
yeah,
and
yeah,
rubella
right,
as
yeah.
well. You can do that. I know
Yeah.
Joe Eisnagel has been able to get RNA and virus off of filter paper transported internationally. Certainly RNA and is quite easy to do that way.
So why do we give live attenuated influenza vaccine to young people but not older?
Well, my understanding is that it works in young people and not older. But Marilda could probably answer that better than I could. I mean, there are other influenza experts in this audience that probably know that data better than I do, so I won't jump in where I'm liable to get into trouble.
I assume it's because you give it to an adult, there's sufficient immunity that perhaps you don't get takes. I don't know. But that's what I'm assuming.
Sorry, can you repeat?
When you give, you attempt to immunize an adult with a live attenuated influenza vaccine, the results are not good. And I assume perhaps because most adults have a wide range of influenza antibody, and perhaps the vaccine doesn't take. But
Yes, this is one of the
Yeah.
explanation for the problem. Yeah. So we are not breached, Larry, but we are more than time. We need to finalize. And so thank you very much for this excellent presentation.